there are several things that I would argue I have oversimplified, but have given you the specifics you needed to know, but never really went back to them in service of let's solve some problems. For example, I distilled the entire year down into just 3 categories, maybe 4, right? There's Newton's laws, there's work and energy, and there's momentum and collisions. Well, there's a lot in all of those, right? A lot, but in service of solving problems, well, we often kind of glossed over some of them or simplified them or stopped thinking about the specific reasons why they existed in the first place. So I want to pick on one specifically because it's for what we need to talk about today, and that is this one. Consider something like this. I place a ball at the top of this hill, give it a little push, and it rolls down to the bottom of the hill. And let's say that this is 1 meter above the ground, and let's say this is 5 meters above the ground. What would be the most likely best use of one of our rules for solving this problem if my intention is to find the velocity of the ball at the bottom? Would we use Newton's laws? No. Would we use work or energy? Why? What's the big giveaway? Okay, so there are clear things here. Change of height, and you can't use force because the ramp isn't uniform, stuff like that, right? So we would probably start in on, well, what kind of energy does it have at the top of the hill? And we would compare that to the energy at the bottom of the hill. When we first introduced energy and talked about potential energy, do you remember I introduced it like this? I put this H minus H naught, and we quickly, me included, stopped writing H minus H naught pretty fast and went with just H. And then, even then, how often have you been required to find out how much energy something has in joules? How often do you generally just use energy as a stepping stone to figure out how fast or how high something goes? Right? It became a means to an end, and we weren't as interested in the actual amount of energy. Well, do you remember where this came from? Like how we got mg h minus h naught? Can I say that that's a no? Because I remember, it's my job to, we were calculating work. And we talked specifically about work against a gravitational force. Like how much work would it take to get the ball from, say, the ground up to the top of that hill if I was just to lift it straight up? Now does it sound more familiar to you? So if you remember, it's a dot product. We would have gone, all right, so if the ball is going upwards, but gravity is acting downwards, the force would be mg, but it's downwards. Remember, we're not talking about how much work I do. We're talking about the work gravity does as the ball is being lifted to the top of the hill. It's going to be integrated from, say, the bottom of the hill to the top of the hill. And I have a dx here, but to get rid of the dot product, I have to put the cosine in of theta. And theta would be the angle between the direction of the force and the direction of my displacement, which I'm pretty sure is 180 degrees, right? Gravity's downwards, but I'm lifting the ball's being lifted upwards. So we would have gotten mg cosine 180, they're all constants, times the integral of dx from h naught to h, which when we work all this out, gives us negative mg h minus h naught. This is the work done by gravity when an object is lifted. It's negative. So then we defined the change in potential energy as minus the work done against a conservative force. All of these words were said to you at one time, but it's been a long time. And we got a value that was in service to being able to solve problems. This was never, ever, how much potential energy the object had due to gravity. This was always the work done against gravity, and always involved a change in height or a change in displacement. But we began to be colloquial about it. I needed you to practice, needed to have drills, and so we said the amount of potential energy it has, mgh, kind of stop putting the delta there. And in service to problems, even if I asked you how much potential energy does it have there, you'd go, all right, mg times 5, so what's the mass of the ball, Ms. Sheldon? What's the mass? Can you give me a number? And you'd say that many joules. But that was never the truth. The truth was always that this was how much the potential energy had changed in going from where it started to where it ended. That's always how it was. I'm bringing it back up because A, time for some review, right? B, this isn't really particularly accurate. For one, there's an arbitrariness to this that I haven't really brought up. We've always kind of suggested that we were in control of the reference level, right? Choose a reference level for your problem. It can be anywhere, as long as you use the same reference level for everything. It probably never occurred to you to say, well, what if the reference level is up here? All my distances would be negative. Would it change anything? No, it's about the change in height. So whether those numbers are negative or positive, as long as I'm measuring them relative to the same height, I can put my 0 on that number line anywhere because it's about the difference in two places, not the absolute location. You follow along so far? Okay. You've come a long way, kids. First, we assume gravity was constant, right? mg, the force of gravity, was constant. Is gravity constant? It's only constant if r doesn't change very much, right? If r changes very much, no longer constant. So as long as we were dealing with things near the surface of the Earth, remember me always reiterating, amount of potential energy based on being near the surface of the Earth? That's why. As soon as you start to get away from the Earth or have a change in R that changes this value, it's kind of hard for us to deal with the potential energy that way. I wish that were the only problem. But what if I want to go, say, to the moon? So I take my little guy, and he says, I'm done with all of you. It's time to go here. Where's the reference level? Do you understand? Our reference level only worked if we were dealing with differences that were relatively minor and allowed for a direct comparison. There's no point of easy reference here. How do I compare the amount of potential energy I may have on the surface of the Earth with the amount of potential energy I would have on the surface of the moon? I can compare the change in potential energy in going from one place on the Earth to another place on the Earth. But to go to the moon, that changes this up, doesn't it? So there are theories on how to do this. And unfortunately, or fortunately, depending on how you kind of want to view this, some theories have to work. Because I want you to imagine, we have done this, right? And everybody kind of thinks it's easy because it's already been done, but we are coming to grips with the fact that it's clearly not easy, because even though we've done it before, we're having a really hard time doing it again. So clearly it's not particularly easy. I want you to consider, how do you know how big to build the rocket? Look, you guys drive cars, right? Your car probably, well, not all kids drive cars, but I'll assume that many of you have seen it done. Your car probably tells you how many miles you have left because you're too dumb to look at the gas gauge. Shockingly condescending. But you understand my meaning, right? It says you've got. In fact, how many of you wait until the little warning thing goes off and says 50 miles till you're empty? I know some of you would never let that happen. It's been ingrained into you. Look, I'm at a quarter of a tank. Fill up now. Always be ready because the zombie apocalypse could happen at any moment. But I also understand that some of you kind of love getting right there to the edge, right? Like maybe it'll go negative if I go far enough, right? So your car doesn't really know, but it knows how much energy is in the gasoline. The guy who manufactured the car and understands the output of the engine, he probably could make a reasonable estimate of the amount of energy contained within gasoline. You AP chemists understand that you can figure that out, right? There are experiments that would demonstrate or allow you to demonstrate the energy per milliliter or cc. What do you think here? All right, cc. I'm asking Emo. I want him to make the choice. I was giving him control here. But you can figure it out, right? Burn a little bit, see how much energy is released. You would know. Now, going someplace, we're all staying at the surface, aren't we? But even if you go up and down a lot, you're not really changing it that much. If we wanted to go from the Earth to the moon, you have to know how much energy it's going to take to get there so that you can build your rocket appropriately. And part of that is knowing what is the change in potential energy between these two places. I'm going to fill that with kinetic energy to get there, right? If I know what the change is, I can probably figure out. Now, the truth is you don't have to get all the way to the moon. You guys know that too, right? You know that you only have to get to about here. There's a place between the Earth and the moon where the force of gravity would be zero, right? Because you'd be close enough to the moon for its pull to have increased while the pull from the Earth is decreased. In fact, it's one of your questions in your homework is to figure out where this plane is. It's a non-stable Lagrangian point. You should find out where it is. It's interesting. See, the more you know. It's not 15 minutes, 8 minutes, I think. Did I get it right? Yeah. All right, so getting back to this, in order for us to understand what we're going to do here, you're going to have to take a bit of a trip with me. We want to find a place that would be a common place, a common relative location that would be the same for the Earth and Moon and Sun and Mars and Jupiter. And so the idea is we want to find a place where the force from the object due to gravity is zero. So where could I go as a person? Maybe not as a person, as a theoretical entity. Where could I go where the force from the Earth would be considered zero? Well, if I look at my force of gravity function, I can only change one of those numbers. I can't make my mass zero. I can't make the mass of the Earth zero. Can't make G zero. But I could make R really big. What we say is that we're going to choose to measure gravitational potential energy from a reference point set at infinity. Something infinitely far away. Far enough where the force of gravity from that object is rendered nil. Now, can't actually get infinitely far away. For one thing, your view of infinity doesn't allow your mind probably to rationalize that, because you can always get further, right? That's the whole thing about infinity. It's always going to be bigger than whatever you could think of because it's the biggest. That's not how infinity works. That's not why it's a concept. It makes for a nice little stupid mental argument, shockingly condescending. more about infinity is a concept of having R be so big that changes in it can't really be reflected in the force. So how far is that? It's not as far as you think. The Voyager space probes, which are pretty far away, are not experiencing hardly any gravity from the sun. They're far enough away. So they aren't infinitely far away, but they're really far away at this point where the force in the sun is very small. So when we talk about infinity in the pragmatic, infinity isn't always the way you guys have conceived it to be. Yes, mathematically infinity is infinitely big. You can't even say it, there's no words there, right? But pragmatically, I always point to this mark I made on the wall in E&M because sometimes you have to wait for an infinite amount of time to go by for something to happen. Remember, we did that once in this class. Drag, air resistance, it approaches the terminal velocity, but doesn't ever get there? Yeah, it does. It gets there almost right away. How long do you have to wait? Long enough to where we're so close to it that changes don't seem to register anymore. That's what it's really about. So, I'm not going to do all the math. I'm going to do a little bit of the math, though. Part of it is because this has a direction, and I didn't talk too much about it, but it happens to be in the r hat direction, but there happens to be a negative sign associated with this too. I don't want to get too deep in the math. But here's what you have to do. You have to say, I want to find the work done in moving something from infinity to, say, the surface of the Earth. Earth becomes the ending point of reference, but since we're doing it for the Earth, we start at infinity. And so the force here is going to be based on the force of gravity, integrated. But there's a dot product in there, and there's stuff about direction in here, and I'm not going to bore you with the details because they're not worth it, because you won't believe me anyways. But we're going to get an answer, and then remember, we have to set that work equal to minus the change in potential energy. Remember all of these factors? So that we get, and this is no longer the change in potential energy. This becomes the absolute potential energy because we are measuring it from an actual reference point that matters. You okay with that? This is a real reference point that is consistent for all objects in the universe. So this reference point matters, and this is the absolute amount of potential energy. What you're not going to like about it is that when you run the numbers, you get that it is minus m1, m2, g over r. R being where you are relative to m1. m1 being your thing causing gravity. So if I wanted to find the gravitational potential energy while I'm standing on the Earth, the actual value would be minus mass of Earth, mass of Shelton, g over radius of the Earth. This isn't a vector quantity, it is a scalar quantity, but, and it should be something you asked me about, Mr. Shelton, what the heck is that negative sign doing there? And our potential energies are considered to be negative. Now, that doesn't make a lot of sense to some people. And I would probably hazard a guess that some of you don't understand why they're negative. Can I give you a good analogy as to why they're negative? Why am I even asking you? I'm just going to do it anyways. I want you to have this semblance like you're in control, but you're really not. You'll nod because if you don't, then I'll probably take longer. And the sooner this gets done, the sooner it'll all be over, right? So I'm not even being shockingly condescending there. I can tell. It's Friday. It was a busy day. The bell's going to ring soon, and you'd like to go do something else. Perhaps anything else. So I don't think that that's shockingly condescending. I think that's realistic and pragmatic. In fact, I'd be surprised, and every once in a while it happens. One of you chuckleheads stays here on a Friday after school wanting to talk to me. And I think, oh, chucklehead, is that okay? Chucklehead's allowed, right? Like the person listening to the video, and they come across this video, and they hear me say chucklehead. Do you think that they think I'm like saying mean things? I'm not saying anything mean to you. Chuckle's funny, right? We could chuckle. If you are chuckling, are you a chucklehead? What do you think, Allie? I need a serious person's render on this one. You think it's okay? Lindley, what do you think? You haven't said anything today. Kaylee? It's shocking? Is it condescending to call you a chucklehead?
I'm gonna leave a comment.
What's that? I think chucklehead works. I like chucklehead. There are other words I could have used after chuckle that would not have been okay. I've heard words. I know things. I hear things. All right. So two friends standing here. One friend allows for the invasive thoughts to enter and pushes his friend into the well. It happens, and it does happen. I've seen it. I see you guys. I see the way you interact. It's not often great, and so friend bottom well. So now he's trapped at the bottom of the well. It's really tall. So there are ways to get out of the well. And he wants to join his friend. And he's maybe a little frustrated, but he's down at the bottom of the well. Yeah, he's fine. He's fine. He's laughing. He's a chucklehead. So he's having a good old time down there. So, now, he could climb the side maybe. Maybe there's a ladder there. And he could do work to get out. He could also maybe apply enough leverage and force to jump out. Right? Give himself a whole bunch of velocity at the bottom, enough kinetic energy so that he makes it just to here, and his friend will grab him. Is that right? Or else he'll fall back down the well. We think of gravity like this point is infinity, and we are trapped in a well. We say that this is our reference level, and that this direction is negative, and that being at the bottom is having a negative amount of potential energy. We're trapped in the well. And to escape the well, we have to acquire enough energy to bring our energy to zero. Right? Because our energy currently is negative. So if we apply enough force or apply enough kinetic energy, we can bring our energy right to zero. That would be just escaping the well. For us, that would be getting out of the gravity well between the Earth. But unfortunately, it's more complicated here. Because just because we could escape the Earth's gravity well doesn't mean we escape the sun's gravity well, right? The moment we get out of the Earth's gravity well, we're now trapped in the sun's gravity well. We have to get out of it as well. Does that make sense? So to see kind of how this works, I want to talk to you about the concept of escape velocity, because it's a good explanation for this particular example. And then Monday we'll finish and talk about how energy works in orbits, which we won't have time to finish today. So imagine you are trapped on the Earth. How many of you have heard the phrase escape velocity before? I was super shocked. Only one person in sixth period. It's only 4 people here. 5 people. Escape velocity would be the amount of velocity I would have to give a person so that they could leave the Earth and escape its gravity. That's what escape velocity means. We're going to make a fake, this is fake, because the truth is this would not be the escape velocity to escape the sun's gravity. So although you might escape the Earth, it would just be to fall into the sun and burn to death. So we're escaping, but we're not really escaping. Follow me? You're not going to get too infinitely far away from the Earth. But this is a thought experiment. Here's how you would use this. Your energy is the combination of your potential energy and your kinetic energy. So the amount of energy, that value we have now for potential energy is absolute and meaningful. So when we talk about this amount of energy, that's not a relative comparison. When you calculate this energy, this is how much you have. It is negative because we have made this measurement relative to a place where you have escaped. If I wish to escape, I would have to have enough kinetic energy so that my total energy would be 0. That's the concept of escape velocity. We don't give things this velocity because first, this is assuming that you give the thing the velocity all at once, right? Use all the energy right away, give all the energy to the person. We tend to, that's like putting somebody on a bomb and just blowing it up, which is really what a rocket does, right? A rocket, however, increases the length of time through which that energy is being applied, so you don't get it all at once. It would be actually more efficient to give the thing the energy all at once, but it probably wouldn't survive the process because it would be too much acceleration, right? It would destroy the object. That's why we kind of dole it out over like 10 to 12 minutes. And that's not even escape velocity, that's just low Earth orbit. So let's see how this might work. It would be the negative mass of me. I'll say mass of you, mass of the Earth, g, over radius of the Earth, because we are starting from the radius of the Earth, trying to get to infinity, plus 1/2 mass of you. I'm giving you the energy. Escape velocity squared equals 0. So if you wanted to calculate the escape velocity, there you go. That's what we would do. So I think you guys could probably put this together pretty quick if you wanted. Notice mass of u goes away. So if you didn't want to find the amount of energy, you could find the escape velocity holistically. But also, this amount of energy would be how much gas you would need, right? This would be the amount of fuel required to leave the Earth's gravity well. You do the mathematics on this, and you get 2 MEG over RE. Can you run that real quick? You know what the mass of the Earth is? 5.96 times 10 to the 24th, and radius of the Earth is 6.37 times 10 to the 6th, and G is 6.67 times 10 to the negative 11th. Can you like mash all those buttons